Mike Arasim with Fair-Rite Products, and I'm here with Dr. Min Zhang from Mach 1 EMC. Hello.
Hi, Mike.
And this is the Ferrite Soft Magnetics Hard Topics podcast. So, Dr. Min, if you want to go over, some of the work and references we're going to go through today.
Yeah, sure. Yeah. Hello, everyone. Pleased to be here. And today, I'm very happy to join this discussion with Mike because we have a few fun slides to show. So before we start, I would like to mention that most of the materials from today's discussion are from these references. The main reference is from Mr. Tim Williams' paper called Using Cable Ferrites for Interference Suppression, and his book, EMC for Product Designers. Mr. Williams now is retired. He used to be one of the most famous EMC experts in the UK, and now he's happily retired. And another paper we reference is from Richard Marshall, who passed away a few years ago. Richard is also used to be an EMC consultant in the UK, and I am a self-employed EMC consultant in the UK. So yeah, you can download all the references in the show notes later. Okay, so yeah, I guess we wanted to start with the theory first. I guess one of the questions that we often get asked from customers, I guess the same with you, Mike, is that how good is my ferrite material, right? Or how good can a ferrite core be in terms of insertion loss or attenuation? And I guess the answer really is it depends, right? As you can see in this slides, if we treat this RLC as a simplified model for our ferrite core material, then you can see that the attenuation based on this equation here really depends on the source impedance and the load impedance. Now, the most challenging thing is often we have no idea in real life what is the source impedance and what is the load impedance. And these, although drawn as a resistive parts, but in reality, they also change because there will be inductive or capacitive components associated with these source and load. So, these also
Sure.
change with frequency. So now if we just look at the ferrite core material, now I'm using a 0431 ferrite from Fair-Rite, and this gives me the impedance against frequency curve. So Mike, do you want to quickly explain to our viewers what we normally need to, if we have a look at this data sheet, what are the most important information here?
Yeah, so it's always kind of the somewhat difficult disconnect, right? Because as you said, we don't always know, the exact details of the circuit. From the manufacturer's standpoint, we try to measure the cores kind of in isolation, deliberately, just to, characterize strictly the impedance of the core. Now, of course, that's never always a perfect thing, right? Because there's going to be some, you know, that snap-it core needs a wire. We don't have a quite the sophisticated test fixturing that eliminates the need of conductors just yet. Um, so what we're looking at is an impedance curve, and for most materials, what you're typically going to be looking for when you're selecting a ferrite is one, the noise that you're trying to suppress, or the frequency of the noise that you're trying to suppress. And the ideal thing is you're looking for a ferrite core primarily that is going to be resistive at those frequencies. So you can see that impedance chart on the right hand side here, and you have your black line on the chart that is going to be just your impedance, complex impedance. And you have your red dotted line. That is going to be the resistive impedance, or the portion of that impedance that is resistive of the part. And then you're going to have your reactance in that blue line there. Now, typically when we're talking about, something like a 31 material, we'll typically rate it between about 1 to 300 megahertz. As you can see, it actually works higher than that. And if the chart were expended lower, you still would have impedance lower. But the important part is that 1 to 300 megahertz. Now, at 1 megahertz, there may actually be better materials in terms of absolute impedance, but typically there's going to be a trade-off in how broadband the material is, so you're not going to be covering those higher frequencies. The other things you might look at too are some of the secondary material characteristics that are relevant to the application. But quite honestly, that's about a 40-minute talk in and of itself when we start getting
Yeah,
that far in there. So
yeah,
primarily, just impedance. Hopefully, it's resistive impedance where you need it as well.
yeah. I guess for me as a EMC engineer, I never really check the inductive curve because, as you said, I treat a ferrite core as more like a frequency dependent resistive part. But is there any
Right.
any occasion where actually people wanted to use this inductive characteristic curve, or most of the time people just look at the resistive curve or impedance curve?
So a lot of times they'll look at just the absolute impedance. Now, when you're talking about really low frequencies, down into the hundreds of kilohertz range, you know, there's no getting away from a lot of that impedance will be down to the reactance. If
Mm,
you look at materials that are functioning down in those hundreds kilohertz, even low megahertz range, they're getting there because uh, the permeability of the material is so high, and that's going to scale that reactance up with the permeability. So, do you necessarily care about it? Uh, you do at times by way of caring about that absolute impedance. Typically,
hmm
there's not going to be too many applications where you're deliberately designing to have a high reactance with a ferrite.
mm,
Well, speaking of suppression applications, now if you're trying to make something like an inductor or transformer, you absolutely want that high
yeah.
reactance, and ideally you want R sub S there as low as you could get it.
Mm, okay. Right. Okay. So that's about the theory of a ferrite core. So now let's move on to the next slides. So yeah, this is interesting because when we are using a ferrite core, especially the cable ferrite core, we use it on cable. And the cables can be meters long or can be centimeters or tens of centimeters long. So, and another tricky thing about cable connection is, again, you don't really know. Let's take a shielded cable, for instance. A USB cable often are shielded, so are HDMI cables. But often what we found is even these cables are shielded, depends on how they terminate the shields. You could have, pigtail termination. And as a result, you can see high level of RF common mode currents on these cables. And then again, as I said, the cable length is one thing, how they are connected to the equipment is another thing. And these cables will resonate, right? They will resonate against the frequency. So here we wanted to demonstrate this by having these slides. And as you can see, this cable bundle showing here, it can be shielded or it can be non-shielded, but regardless, right? Here, when we talk about impedance to connect a connection, right, termination impedance, we are talking about the common mode termination. So, for example, in this case, the ZL representing the load termination, it is a common mode connection. So, for example, if it is connected to a very large metallic equipment, we often treat this connection as a low impedance. But if it's connected to a plastic small component, and then we often treat it as a high impedance. So again, we're having these uncertainties that we don't know the impedance uh, on both sides of a cable connection. So where shall we put the ferrites? That's often the question we got asked. Now, on top of that, there's another issue, which is the voltage standing waveform, right? So here I just have this curve again, showing you the input impedance against frequency, and you can see this is showing a resonance behavior of a cable which is 0.5 meter long, and this impedance is calculated when we say a open circuit ZL. So that means, here the load impedance, as we said, is a high impedance connection. But what if this is a low impedance connection? Then you would end up having something like this, right? So that would be your short circuit impedance curve. So really, again, you just have all these uncertainties, and when if you look at the equations we mentioned earlier on, you want the Fair-Rite to be most effective when you put the Fair-Rite in a lower impedance point. But because of this varying, the impedance always varies with frequency. So it's presenting a big challenge when we try to use Fair-Rite. I guess this slide really shows you what we mean. Okay, so in order to demonstrate that, in order to demonstrate this impact, we have this Fair-Rite test setup, right? And this is a very simple jig that I built, and I'll quickly explain this impedance or resistive network. The idea is very simple, right? So here, as you can see in this setup, we have this a spectrum analyzer and with a tracking generator function. So we're using the tracking generator function as a source, and these source often has a 50 ohm impedance, and the spectrum analyzer also has a 50 ohm input impedance as well. So we've got 50 ohm and 50 ohm here. So if you work out the math here, then you can quickly calculate that this channel showing here will have what we call high impedance path, which is 180 ohm, and this path would be 18 ohm, so representing a low impedance path. And with a simple jig like this, we can demonstrate the effectiveness of a Ferrite core, and we can demonstrate a few ideas which we will show you later on. But before we move on, I would like to ask Mike. So this is my simple jig to test a Ferrite core's performance, right? Simple as it is, you can always argue that the way I build it is quite cruel. You can always make a better one by having it printed on a printed circuit board and in a shielded box. So when you guys test a Ferrite core, insertion loss or attenuation, how do you test it?
So typically when we're doing testing in-house here, again, because we don't necessarily have a target circuit that we're trying to attenuate a signal in. So, I mentioned earlier that we really just try to test the core kind of in isolation. So that means we keep the same standard test method to the degree that we can anyway, based on the frequencies we're trying to operate. But we keep a relatively standard test method. So the workhorse of the measurements we make for suppression components is an impedance analyzer. So we'll use different analyzers depending on what frequency. Typically it's an Agilent or Keysight 4990 or 4991. That's a 50 ohm loaded impedance analyzer, just single port. Now we have a test fixture that we use, well, a couple different test fixtures that we use depending on if we're talking about on board or if we're talking about a on cable type component. This is the case here. And in terms of conductor, it's important that we keep the same conductor diameter consistent between part to part. And the wire length, we are going to keep that as short as we practically can, because ultimately you could put a pretty long piece of wire and it really looks like a pretty good ferrite when you're looking at it on an impedance analyzer.
Exactly.
So we try to minimize that to keep the measurement of the ferrite. that aside, I mean, from actual, kind of a more similar test setup to this, I guess I would say is what we do when we're characterizing some of the free space type devices. So if you talk about something like a plate or like the flexible ferrite sheets, then we switch to a vector network analyzer and start looking at that type of measurement, but we're using different coils. We have some of the test methodology outlined on our website, what we use for that. But just different, fairly basic, really loop-to-loop coils with the sheet in between or perpendicular to, depending on what type of test method. And we just looked at reflected and emitted coefficients, S parameters on there to calculate
Hmm.
that. But yeah, I mean that's pretty much what we do internally. We've done some stuff like this, maybe not really as I know as crude as you said, ours was
Hmm.
probably cruder, but we've tried to doing,
Yeah.
anything similar like this, but that's typically more from a customer question point of view or, just a test example kind of thing, but it's not something that we do on kind of a standard basis because we don't
Hmm.
have a target circuit really.
Yeah, exactly. I think this also reminds me that for filter companies, like companies that sells a filter as a solution, they often test again 50 ohm input impedance, source impedance, and 50 ohm load impedance. But then often they also have to do that zero point 0.1 ohm as the source and 100 ohm as the load, and then they do the 100 ohm as the source and zero point 0.1 ohm as the load, trying to do a different combination. But as we explained, that just trying to go to the extreme, but in reality, we never know, right? We never know what's the source impedance or the load impedance. Okay. So yeah. So let's have a look at this simple fixture I built, and today actually I have it set up. So now if I just switch to the camera, so we should be able to see this live. Yeah, let's have a look. Now you can see this is the fixture that you see in the presentation. And as you can see, I'm connected to a spectral analyzer with a tracking generator function. Um, Here we already got two traces plotted. Now it is worth mentioning that before I place the ferrite on this cable, I need to do a normalization first for the exact reason that you just said, because we are measuring the frequency, in this case, up to about 500 megahertz. Therefore, um, the cable length, this wire length, being a few inches long, introduces about 60 to 80 nanohenry inductance. And you can work out at 400 and 500 megahertz, the impedance of it actually dominates. So we definitely need to normalize that out. And as you can see here, I
Sure.
place a ferrite core on this cable, and I can see the well, in this case, insertion loss or attenuation against frequency. This is a 31 material I placed, and I can even see using a marker function. Uh, yeah, I can see that it's most effective at about 40 megahertz. 40 megahertz, it gives me about 14 dB uh, attenuation, and I can easily swap different ferrite core materials on the same wire. Okay, and the you can see there's a yellow trace, and that yellow trace is the 75 material I placed on the wire earlier on. So really, this is a very effective way of saying how different materials will have different impedance at different frequency. So this
And this
shows you
is
that
this
you
is
can
all in that low impedance test setup, right?
exactly, yeah. So we have two channels. So currently I'm using the 18 ohm, which is the low impedance channel, and we also have a 180 ohm channel on top, which is not connected at the moment. Then as we'll show you on the slides later on, we can do different tests using this simple fixture. So now I'm gonna switch back to my presentation again. Okay, so yeah, now with that set up, and now here I present some results, okay? And so I'll just quickly explain. So you can see I marked each curve with the Fair-Rite core part number, and also I highlight whether it is tested on the low impedance channel or the high impedance channel. So for example, if we just look at the same material, again, same part, 75 material, which we know they're often very effective in a lower frequency range. But you can see that in the lower impedance path or channel, it works most effectively, right? At this frequency, perhaps a few hundreds kilohertz, that it can reach about 12 dB attenuation. Whereas if you have a high impedance circuit, then you can maximum you can achieve is about 2 dB. So that often explains, sometimes engineers said, well, I tried the right material in the right frequency range, but yet I only see 1 or 2 dB reduction, and that may explain, right? The chances are he or she has a high impedance circuitry there. Therefore, at this low frequency, you put a Ferrite core, it simply cannot achieve the same effect as compared to a lower impedance circuitry. And same applies for the 31 material. Again, you can really see the difference in terms of frequency performance between the two material. But I think the most interesting thing about this curve is where you can see here, there's a crossing point here, right? And this crossing point here is about 400 megahertz in this case. And if we just compare these two curves, both a 31 material again, and one is in the lower impedance and one is the higher impedance. So at higher frequency, we can see that for the higher impedance circuit, the attenuation, insertion loss actually is higher than the low impedance circuit, right? So this is where they cross, and then here the higher impedance path actually shows better performance compared to the lower impedance path. So again, this is really because
the other thing I noticed too, the frequency on the low impedance path looks to be shifted. The peak attenuation frequency looks to be shifted down into, I don't know, maybe 50 megahertz, 30 megahertz, somewhere in that range. Whereas it looks like you're up over 100 on the high impedance.
That's right. Yeah, that's right. It really shifts. It depends on the circuitry, and here is again when we set 300, 400 megahertz. If you look at that wire made, a few inches long, then the impedance of the wire perhaps already exceeds about 150 or 200 ohms. So in that case, if you have an 18 ohm resistor network, really is compared to that wire length is nothing. Whereas 180 ohms still, they are comparable in that frequency range. Therefore, the 180 ohm channel actually performs better. So this is something quite interesting from this experiment. Okay, so and then next, this is something really interesting. So again, I'll hand it to you, Mike. Can you quickly explain, right? When we are using multiple term configuration on a Fair-Rite, what do we need to consider, right, when we're making a few terms? Is it like the more terms we make, the better?
It can be. So, I mean, the very obvious, without being too funny, thing to consider is whether the inner diameter of your core can actually fit multiple turns. But yeah, I mean, so at the lower turn counts, and especially speaking at the lower frequencies, typically more turns is going to be better. You'll get a higher impedance value, but that does come with some drawbacks as you start increasing that turn count. You start wind up, you wind up getting parasitics basically, and you're going to be decreasing the effective bandwidth of the ferrite. So you're going to wind up with, at the very, very low end of the frequency range where we'd maybe rate that ferrite. So take 31 material, for example. If we're looking at 1 megahertz, yeah, you're going to be getting significant increases in impedance with each turn that you put on that core. But once we start getting into, depending on the core size, when you start getting into, 3, 5 more turns than that, you're going to see that same increase in impedance at low frequency, but around your peak impedance, which, by the way, the frequency of that peak impedance is going to be shifting lower and lower in frequency, you're going to notice the impedance curve gets very peaky. So you're going to have, at some really, really specific frequency, massive, massive impedance that you're registering on an impedance analyzer. But you'll notice that impedance curve is going to just drop like a rock right after that frequency. So you may wind up going backwards at the higher frequencies from having too high of a turn count on the core.
Mm. Yeah,
And
indeed.
here's
I
where
mean,
you
this.
give us
Mm,
the special technique.
yeah, um, yeah. This then perfectly demonstrated what you just said. So first thing we noticed is now it has about 35 to 40 dB attenuation compared uh, with previously, with 1 turn. I think we achieved about 10 to 12 dB on an 18 ohm channel. So that's definitely a significant increase in terms of the insertion loss. However, one thing we noticed that it's definitely shifting to a lower frequency point, as you mentioned. And also we notice this very sharp drop, as you said, here as well. So it's quite peaky, as you said. Um, and the reason is because of the parasitic capacitance as you introduce more turns. So in this case, I have to say, to mention that it is a 5-turn configuration, so quite a lot. Therefore, you start to introduce the 10-to-turn capacitance. And these capacitors are quite small, but at higher frequency, hundreds of megahertz, now they started to 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 make a difference. Hence, we see this peaky kind of performance. Now there are ways of minimizing the stray capacitance. One obvious, and easiest way of doing it is you try to space this winding, right? So in this case, I had 4 or 5 terms, and I put them all together. Obviously, this is the worst case when it comes to 10-to-turn capacitance. You can always try to spread them out around the circumference, but that can lead to somewhere, but not 100%. You still have that capacitance impact. Another way of doing this is I show here is from a paper back in the 1980 or 1976. It's a very old paper, and the author introduced this super toroid winding techniques. As you can see here, again, this is about 5-turn configuration. And this actually can give you a better performance in the higher frequency range, as we demonstrate here. So here we have same number of terms, right? One we just wound as normal winding configuration, and then this one we use the super toroid configuration, as you can see here. And then the yellow trace shows much better performance, especially in the higher frequency range you can see here. So that's really the big improvements by having this configuration. And the reason for that is because if you look at this winding, right, and if you look at the maximum voltage of the winding, really is between this point A and point B. And by having them separate apart, right, they have the longest distance between these two parts. Therefore, you try to minimize the capacitance between A and B. Therefore, you reduce the E field, the electric field impact uh, 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 of this configuration. Compared to this configuration where the winding are next to each other. So the highest voltage, and then you have the highest capacitance. Therefore, you have the highest coupling, E field coupling. So that's really it is. Okay. So yeah, I mean that's everything we would like to discuss for today. As you can see, the the fixture we made is a very useful tool to demonstrate a few ideas, right? As we can see here. But of course, they can be used for other kind of performance analysis, right? For example, different materials comparison or different size. We haven't talked about the size. The size actually, when it comes to using Ferrite core, size matters, and things like that. So hopefully, maybe next time we'll do another podcast focusing on the size selection and other things.
Yeah, no, I think that'll be excellent. And why not wind like that when it has a name like super toroid? I mean,
Yeah.
I'd use it even if there wasn't an advantage just being called the super toroid.
Okay.
Yeah, so that's fantastic. I think that, like you said, that about wraps it up for today.
Okay.
Thank you everybody for watching. Thank you, Dr. Ben, for being a part of this, and I look forward to our size discussion next time.
Yeah, definitely. I mean, if you have any feedback from our audience, please let us know because we're also learning through the process. So yeah, feel free to drop us an email.
Yeah, yeah, absolutely. It's yeah, like you said, always learning every time you get a new application or a new problem. As much as you don't hope for problems, but sometimes they're very useful learning tool, and always learning.